Hello everyone, this video covers sections 4.2 to 4.5 from the textbook. The whole chapter now we're gonna switch from discrete to continuous random variables. So in a sense we're gonna do the exact same thing we did in chapter 3, except that now we're gonna focus on continuous instead of discrete random variables. So let's start with the following definition. Let y be any random variable. The distribution of the function y, denoted by capital F of y, is such that f of y is equals to the probability that capital Y is less than or equals to y. So notice that at this point we still haven't stated that this is continuous. So this is true in general whether the function is discrete or continuous. So the distribution function, which most of the time is actually called cumulative distribution function, is denoted by f of y, capital F of y, and the definition is technically just the probability that capital Y is less than or equals to y. For example, let's say that y is a binomial distribution where n is equals to 2 and the success probability is 1/4. Remember that this means n is 2 and p is 1/4 if this is a binomial. Now remember that the mass function for this is equals to 2 choose y and then 1/4 to the y, and then the failure probability, which is 3/4 to the 2 minus y. Okay. So again, this is not new, and we have calculated this before. The probability of 0, remember, is 2 choose 0, 1 to the 4 to the 0 power times 3/4 square, which is equals to 9/16. If you do p of 1, well, this is 2 choose 1, 1/4, 3/4 to the first power, and this is going to be 2 times 1/4 times 3/4, and this is equals to 6/16. And you can check also the p of 2 is the following. So again, this is not new. Everybody should know how to do this by now. So we have done this multiple times. And remember that this is called the probability distribution, while capital F is going to be the cumulative distribution function. Right, so remember that by definition, f of y is supposed to be the probability that capital Y is less than or equals to y. Notice that the only values we have for y here are 0, 1, and 2. Those are the possible values for y. So therefore we do a graph, and let's say this is 1, it's 2, and 0. So notice that you're going to have a state function because the values for y are whole numbers, 0, 1, or 2. Those are the possible choices. So let's say that this is equals to 9/16. Okay, and then the other one is 6/16, but if you add it up, this value will be now 15/16. We'll go from here to here, and then if you add, obviously this is not the scale, but one more, it will be 16/16. So it will be this, and this part will be 0, because you cannot have any values less than 0 for the binomial. So therefore this is the graph for capital F, and if you write an actual equation, it will be as follows. This will be equals to 0 if y is less than 0, which is this part, and then this will be 9/16 if you go between 0 and 1, which is this one, and then it will be 15/16. Okay, 15/16 if you are between 1 and 2, and it should be 1 if y is more than equals to 2. Now, it should not be surprising that the last value has to be 1. If you are adding all the probabilities, remember it has to add to 1. So therefore, the last value always has to be 1. When you add all the probabilities, you should get 1. Which is technically what the following theorem is stating. So if f of y is a distribution, then f of minus infinity, which is the limit as y goes to infinity, or f of y is equal to 0, which you can see that's the case here. In this one, the limit as y goes to infinity should be 1, which means if you add all of them, it should give you y. Now, number 3, it should be obvious that f of y is non-decreasing. So non-decreasing in this case means that f of y1 has to be less than or equals to f of y2 if y is less than y1, which it should be obvious from here. If we have f of say 1.5, which is in here, clearly it's going to be less than or equals to f of 2.2, which is in here. So you can see this is a non-decreasing function. Okay. Now notice that this example we just used is for a discrete function, which means the cumulative distribution function, you can have it for discrete functions too. So now we're going to switch from discrete to continuous, but the definition is going to stay the same. But for continuous functions, we're going to use calculus instead of algebra, which brings us to the following definition. A random variable y with distribution function f of y is said to be continuous. Okay, so now we're going to jump to continuous if f of y is continuous between minus infinity to infinity. Okay? The next definition is very, very important. In the discrete case, we used to have p of y. So for the discrete case, we used to use p of y to find the probabilities. We also call it a mass function or the probability distribution. In the continuous case, which I'm going to use CTS for continuous over and over, we're going to use now f of y, and it's going to be called a density function. So this definition is very, very important because you have a distribution function, the derivative of the distribution function is going to give you the density function, which is the one we're going to use to find probabilities, or this is the analogous or the equivalent of py for the discrete case. Okay. Notice that this is equivalent to have the following. So this implies the cumulative distribution function is equal to the integral from minus infinity to y of f of t dy. And if you look at this closely, we have something like this in calculus 1, the fundamental theorem of calculus, the derivative of this will cancel each other out, and you will end up with f of y. So you look to the fundamental theorem of calculus, you will get f prime of y is equals to f of y. Which brings us to the following theorem, which says the following. So these are the properties of a density function, which you should remember for the rest of your lives. So here it is. If f of y is a density function for a continuous random variable, then the following is the case. f of y has to be always positive in the whole interval, and the sum of, you can think of this, all the probabilities has to equals to 1. One of the most famous examples of density functions is e to the minus y from 0 to infinity. Notice, by the way, that this doesn't mean you always have to go from minus infinity to infinity. This is possible, but you can go only from 0 to 1 or 1 to 10. It depends on what the variable you have. But notice here that you use these values. This is always positive, so the first one is satisfied. And for number 2, the integral from 0 to infinity of e minus y dy is equals to negative e to the minus y from 0 to infinity. Remember that when you plug the limits in here, since this is going to infinity, this is in the context of limits, but since you did this before in calculus many times, so this will be minus, it will be 0 minus e to the minus 0, which is technically just 1, and the whole thing is 1. So therefore this is a density function for some random variable, which we actually will see in detail later, probably next week for this one. For now, this is just a good illustration of what a density function is. Now let's do an example from the book. And the book, they have the following. It tells you this. So let's say we have the following random variable, y, which it has the following density function, where here k is a constant and y only goes from 0 to 1. So the first part, this is a typical question, is what is the value of k? Right, so what is the value of k? Okay. That will make this a probability function. Well, all you have to do, remember, is you need to integrate from 0 to 1. You can take the k out. This is technically y minus y squared dy. So this will be k times the integral of this, which is y squared over 2 minus y cubed over 3. And this will go from 0 to 1. And you want this to equals to 1. Otherwise, it's not a density function. So if you plug 1 in here, this will be k times 1/2 minus 1/3, and this has to equals to 1, which means you have k times 1/6 equals to 1. So clearly k has to be equals to 6. Part B, it's asking you to find what's the probability that 0.4 is less than equals to y is less than 1. So by definition, this is going to be the integral from 0.4 to 1 of the density function, which now we know is 6 y times 1 minus y dy. Which, now that we know what the integral of this, we're just going to multiply that by 6. So this will equals to 6 times y squared over 2 over y cubed over 3. But now it's going to go from 0.4 to 1. So therefore this is going to be 3y squared minus 2y cubed from 0.4 to 1. And you should check that this is just equals to 0.648. Notice that here it doesn't matter if this was an equal sign or not. Why? So the reason is because this is a continuous function. If this was not continuous, then that will really matter. But for continuous functions, this doesn't matter if you have the equal sign. Right, part C, The question is this: what's the probability that y is less than 0.4 given that y is less than 0.8? Now, if we use the conditional probability formula, which we learned since, I believe, chapter 2, by definition, it should be the probability that y is less than 0.4 and y is less than 0.8 divided by the probability that y is less than 0.8. Now, less than 0.4 and less than 0.8 is just the probability that y is less than 0.4, and then this will be less than 0.8. And then you just have to find the two separate integrals. This will be the integral from 0 to 0.4 of the density function, which is 6y 1 minus y dy. Well, this one will be the integral from 0 to 0.8 of 6y times 1 minus y dy. And once you check, this is equals to 0.393. Note, and this is mostly related to, is more related to stats than probability, but we're going to use it a few times. There's something called the the Pitt quantile or percentile, and this is exactly what we've been doing. So we're going to use the same notation. Remember that if we have f of y, that's the density function. So if we have f of, okay, you can call it phi of p. Therefore, by definition, this will be the probability that y is less than or equals to phi of p. So that's not new. But if this is equals to p, where p will be obviously between 0 and 1, then this will be called the p quantile or percentile. And usually what that means is that they give you this value, and from here you have to figure out how far you have to go to get to this value. So for example, if I say find f of phi of point A, that means that there has to be a value which is going to be called phi of point A, such that the integral of the density function has to be equals to point A. That's all it means. Okay, and we'll do a lot of examples with this notation very soon and in the future. Right now, let's jump to section 4.3, which is going to be the expected value for continuous functions. We did expected values before, so this is not new. The only thing new is that it's for now continuous functions. Now, just to refresh your memory, in the discrete case, the expected value of the random variable y was equals to the sum of y times p of y. So in the continuous case, the summation is going to be replaced by the integral. So notice the similarity, and the p of y is replaced by the density function f of y, and you just have to integrate. So if the integral exists, then this is expected value. Now in reality, you want to be more technical. The expected value is supposed to be with the absolute value in order for you to say that it exists, but we'll just go with the definition that the book has. Now, just like before too, you can have a function of y, and you can find the expected value of the function of y by just multiplying. Instead of multiplying by y, you multiply by the function of y, and this will give you the expected value of this, which could be x squared, x cubed, y cubed, y to the 4, the square root of y, whatever you want. So let's do a couple of examples here. All you need to do is integrate, and you may have to review the integration techniques from calculus 1, like substitution, integration by parts, and so forth. But all you have to do is multiply by y and then integrate. So for example, in the previous page, we have the following density function. Remember the f of y was equals to 6y times 1 minus y, and it was only true between 0 and 1. So therefore, if you want to find the expected value of this random variable, this will be the integral from 0 to 1 of y times the density function, which is 6y times 1 minus y dy. So in this case, you can take out the 6, so this will be the integral from 0 to 1 of y squared minus y cubed. And then this will be 6 times y cubed over 3 minus y4 over 4 from 0 to 1, and whatever that is, which should be straightforward to calculate. We also did this example before. Remember the f of y e to the minus y. If you go from 0 to infinity, this is also considered a density function. So what will be the expected value of this one? So by definition, this will be the integral from 0 to infinity of y e to the minus y. And for this one, you have to do a integration by parts. If you use integration by parts, you should get minus y e to the minus y, and then minus e to the minus y. Then you plug the limits of integration from 0 to infinity, which again, this is a calculus problem. Remember, this part will give you 0, so it will be minus 0 minus 0, and then minus, this will be 0 minus 1, and in this case, the expected value is just 1. By the way, if you need to find the variance, which you also need to find the variance for some of these variables, the variance, remember, by definition, is the expected value of y squared minus the expected value of y squared. So therefore, we already got this, which is equals to 1. So you want to find the variance, you need to multiply by y squared first, do the integration by parts twice, and whatever you get will give you this value, and you subtract that minus 1 squared. That will give you the variance. Same idea in this case, if you needed to find the variance. Okay. All right, so let's do one more example. The proportion of time y that an industrial robot is in operation during a 40-hour week is a random variable that has the following density function. The density function is the following: f of y is equals to just 2y between 0 and 1, and 0 otherwise. So in part A, they ask you to find what is the expected value of y. So remember, by definition, this will be the integral from 0 to 1 of y times 2y dy, which in this case is just the integral from 0 to 1 of 2y squared dy, which would be 2y cubed over 3 from 0 to 1, which is just equals to 2/3. Like I say, now to find the variance, you need to figure out first what is the expected value of y squared. And again, by definition, now it will be the integral from 0 to 1 of y squared times 2y, which will be the integral from 0 to 1 of 2y cubed dy. And you should check that this is equals to 1/2. It's straightforward to check that. Therefore, the variance of y is going to be the expected value of y squared minus expected value of y squared, which in our case it will be 1/2 minus 2/3 squared, and this equals to 1/18 once you simplify everything. Now for part B, we're gonna define a new random variable. So let's say that the profit that the rabbit is making is given by the following function. The profit is defined to be 200y, which is the original variable, minus 60. And the question is asking you to find the expected value of x and the variance of x. Now, recall we did this in chapter 3, and I told you you were going to use these formulas over and over. So let me just write it here on the side. And the expected value of ax plus b is the same thing as a expected value of x plus b, and the variance of ax plus b just equals to a squared, the variance of x. So we have these formulas. So in our case, this will be 200 times the expected value of y minus 60. Now the expected value of y that we got was 2/3. So that means this will be 200 times 2/3 minus 60, which is, it is, I think, 200/3. Okay? So just check on that. And therefore the variance, you use the formula, so this should be 200 squared times the variance of y. So in this case it will be 200 squared. The variance we got was 1/18. So therefore this will be, once you simplify, just 20,000 divided by 9. So after now we have done, we have deal with continuous random variables in general. So from now on, which means beginning section 4.4, we're going to talk about specific random variables, just like we did in chapter 3. If you recall, in chapter 3, we talked about the general properties of discrete random variables, and then we went to specific variables with the binomial, geometric, hypergeometric, and so forth. So now we're going to do the same thing, but for continuous variables. And the first one we're going to talk about is called the uniform distribution. Okay, so now let's go to section 4.4 and talk about the uniform probability distribution, which is the most basic continuous random variable. The definition is the following. You have theta 1 less than theta 2, where these two are just two constants. A random variable y is said to have a continuous uniform probability on the interval between theta 1 and theta 2 if and only if the density function is given like this. Okay? The logic behind this density function and why it's called uniform is the following. If you have, you can say, the number line, and you go from theta 1 to theta 2, so notice the length between this is going to be obviously theta 2 minus theta 1, so that will be this length. If you want this to be a density function, the whole area has to equal to 1, so therefore the height has to be 1 over theta 2 minus theta 1. And the reason why it's called uniform, notice how you have different sub-intervals. All of them have the same area. So it is equally likely for, let's say that this is how long it will take you to see a doctor or to see somebody in the DMV. The distribution is uniform. It's equally likely that you will see the first 5 minutes or the last 20 minutes. And like I say, this is a random variable, so it must have a expected value and must have also a variance. And the expected value, remember, is the integral, and this is one of the easiest ones. You should just check this. This is just theta 1 plus theta 2 divided by 2. That's the expected value. And the variance, which remember we're going to call the variance sigma square. The expected value is going to be mu. And you should check this. This is just, again, basic integration. It should be theta 2 minus theta 1 squared divided by 12. So I highly recommend that you verify this by yourself. At the very least, you should memorize this result for the uniform random variable. Okay, now let's try an example using this distribution. All right, so let's say that y has a uniform distribution from 0 to 1. So therefore this is theta 1, this will be theta 2. So this automatically implies that the density function is going to be 1 over 1, which is the most basic thing you can have. So therefore you want to find f of y. This is going to be the integral from 0 to y of just 1 times dy, which technically is just equals to y. And this is going to be the case if you are between 0 and 1. Otherwise, if this will be 1, automatically y is more than 1, and 0 if y is less than 0, pretty much. Okay. So this is part A. Part B is asking you to find the probability that A is less than equals to y less than equals to A plus b. There are two ways to do this. You can just use the cumulative distribution function, which in that case it will be f of A plus b minus f of A. And notice that this is just technically f of, this will be A plus b minus A, which would be give you just b. Or you can do it will be the integral from A to A plus b of 1 dy, which will be technically just y from A to A plus b, and this will give you again just b. So either way. All right, let's do one more example. So here, let's say that the time it takes to for a truck to put concrete in a highway is uniformly distributed. So it's uniformly distributed with theta 1 equals to 50 minutes and theta 2 is 70 minutes. So this is how long it will take a truck to haul some concrete on the highway. So therefore the density function for this one, it should be 1 over 70 minus 50, which is just 1 over 20. And this is true between 50 and 70. So the question is, what's the probability that the cycle time or the time will exceed 65 minutes, given that you know that the cycle time exceeds 55 minutes? Okay. Or in other words, what's the probability that it will take more than 65 minutes to put the concrete, given that you already know it took more than 55? So hence, by the conditional probability formula, this should be the probability that y is greater than 65 and y is greater than 55 divided by the probability that y is greater than 55, which is the probability that y is greater than 65 and the probability that y is greater than 55. So then we use the definition of the density functions. In this particular case, this will be the integral from 65 to 70 or 1 over 20 dy, and this will be the integral from 55 to 70 or 120 dy, which notice that the integral of 120 over y is just 1 over 20 is 120 y. The length of the interval is 5, so technically it will be 5/20 on the top, and on the bottom this will be 15/20. And when I just simplify this is just equals to 1 over 3. Now finally, for this problem, if you wanted to find the expected value, remember that the expected value for a uniform is just theta 1 plus theta 2 over 2. So in our case, this will be 50 plus 70 divided by 2, which is 60. And the variance is equals to, the formula is right there, is theta 2 minus theta 1 squared over 12. So in our case, it will be 70 minus 50 squared over 12, which will be 20 squared over 12. And that should be around 33.33 or 100 over 3. And that's it for the uniform. As you can see, it's straightforward. The last one we're gonna do is one of the most, if not the most important ones. It will be the first time we try it, and that's the normal distribution. So that will be the last section we'll do. All right, so the last section that we'll be covering is section 4.5. We're going to talk about the normal probability distribution. This is the density function, and this is probably one of the most, if not the most important distribution in the whole class, or in all of probability. You'll see why as the class progresses. If you do the graph of this, you have the mean on the middle. Notice that this keeps going forever. This is also the empirical rule, and remember the area has to be 1, so that means this has to be 0.5, has to be 0.5, and since this is a random variable, the expected value obviously is mu, which is already in the formula, and the variance is sigma square. Now, in theory, to find any of these probabilities, all you have to do is integrate using the cumulative distribution function. However, that's not easy to do actually. So that's why we have tables to find the probabilities. For example, if I ask you what's the probability that y is greater than 3, for example, this by definition is only 3 to infinity of this. Okay, and let's say here the value for mu was 5, and the value for sigma was 2. So then this value will be technically 4, will be e to the minus y minus 5 squared over 2 times 4, which will be 8 dy. Now to integrate this is not that easy. Actually, it's pretty tricky to do the actual integration. So that's why we're going to use tables instead to give you these values. Now specifically, we're going to start with a standard normal distribution, and this is the most commonly one used. And if something is not a standard, like this is not a standard, you can always change it to standard. Standard means that the mean is 0 and the standard deviation is 1. Now let's see how we use the table to find some probabilities. Let's say that you want to find this probability. So let's say this is an example. So we're going to focus on the standard normal because the table only has a standard normal values. So let's say you want to find the probability that z is less than 1.5. Okay. Now the first thing you should always try to do for this is draw a graph. It's not mandatory, but it will make life easier. So this is a standard. 0 is in the middle, so this is 1.5. So less will be this. So that's what you want. Now you look to the table, which is in table 4 on the back of the book. And it looks like this. Right, so now it's very important that you know how to read this table. And when you do the test, you use this one specifically. There is several versions of this table, and each of them is read in a different way. The one you have in the book, if you look to the picture, is always going to give you the area to the right or whatever z value you have. So if this is value 1, then you're good. But if you want this, you have to subtract 1 from this one. Or if you want a specific part only, you have to do 0.5 minus that. So this is what I mean. 1.5, we look to the value of 1.5, is this number right here. So that's the area to the right, but you don't want the area to the right, you want the area to the left. So this one is 0.0668. So therefore this probability is going to be 1 minus 0.0668, which is 0.9332. Now remember, in theory, this is also f of 1.5, which is the integral from minus infinity to 1.5 of the density function, which again is not going to be that easy to integrate. So that's why we're just going to rely on the tables. All right, so let's say this is part A. So part B, if I would ask you what's the probability that z is greater than 1.5, well then greater than 1.5 is exactly this part. So therefore, in that case, then whatever you get from the table, which was this value, the 0.0668, that's the answer. Okay, 668. Now using the same information, let's say that part C is the following. What's the probability that z is between 0 and 1.5? So then in that particular case, now you only want this area in blue. But remember that this is 0.5, so is this. So therefore, if you want this part only, this plus that has to be equals to 0.5. So therefore, this will be equals to 0.5 minus 0.0668, which is 0.4332. And that's it. All right, let's do another example. Let's say you want to find the probability that minus 1 is less than z less than 1. So if we do this, then all you have to do is look to 1. Actually, before you do that, you should always draw a graph of what you want. So you have 1, negative 1. So this is the part that you want. Remember that the table is going to give you this part. So that's what you get from the table. You look to 1. So you look to 1, the table tells you this is 0.1587, which is this value right here. Okay. So now there are several ways in which you can figure this out. In this case, notice that this is symmetrical, so you can find this and multiply by 2. So this is twice the probability that z is between 0 and 1, which is the kind of problem that we did here. So in this case, it will be 2 times 0.5 minus 0.1587, which is around 0.6826, or if you round it up, this is 68%. Okay. Now the book does the next problem, but you should check this yourself. Let's say this is part A. Part B, the book does this one, the area or the probability between -2 and 2, and this is around 0.95 or 95%. So now the reason why I'm doing this specifically is that this is the number for the empirical rule. Okay. Remember, you move one standard deviation, you have 68%. Remember that the standard deviation is 1, so this technically means 1 standard deviation to each side. This is 2 standard deviations, that's 95%. And if we would have done 3 standard deviations, remember you get 0.97.1%, or something close to that. So you should just give it a try. But for right now, the easiest way to find any probabilities to use the table, or if you have a TI 83 or 84, you can use it too. I can show you in the class how to use the calculator, or you can just use the table. Okay? Now let's do a word problem, but it's exactly the same idea. So let's say that the problem says the following: the GPA for a large population, so it says the GPA, let's say, are normally distributed, okay, with mean is equals to 2.4 and the standard deviation is equals to 0.8. Okay. So then it says, what fractions of students will have a GPA in excess of 3.0? So technically the question is, what's the probability that y will be more than 3.0? Now notice that this is not a standard because the mean is not 0 and the standard deviation is not 1. So therefore, to change to standard, we're going to use the following. C will be equals to y minus mu over sigma. So in this case, this will be equals to 3.0 minus 2.4 divided by 0.8, and this is equals to 0.75. So therefore, this is equivalent to finding the probability that the standard normal is more than 0.75. So then you should look at the table. 0.75 is here. Greater means to the right. So remember, this is the value you will get from the table. And you look to the table, this is actually 0.2266. So therefore, this is just 0.2266, and that's it. Obviously, if the question was the probability that y is less than 3.0, once we have done part B, this is 1 minus the probability that y is greater than 3.0. So in this case, it will be 1 minus 0.2266, and that equals to 0.7734. Finally, let's do an example where you had to, excuse me, read the table backwards or find the inverse value. And this is what I mean. Let's say that you want to know what will be the value, and this is actually related to the percentiles too. So let's say z0, so that the probability to the left of that side has to be 0.975. Okay. So which value will give you this probability? So then we do the tables, which I mean the graph, which I told you already useful. That means you have some z value here, where this area is 0.975, which means the area to the right, which is the one you have on the table, is 0.025. So all you have to do is look for that value in 0.025. You will see is exactly right here, which corresponds to 1.96. So therefore that came from 1.96. So that means that Z0 has to be 1.96. Right, so this is the first look at the normal distribution. We're going to definitely look into this multiple times. That's it for now.